In this lesson, I'm going to introduce you to Taylor's theorem, which allows you to predict the shape of any function given nothing but its derivatives. When I first saw Taylor's theorem, I was pretty impressed because I just didn't think this was possible. But the general idea is, as long as you can find the derivatives of some function that you know is continuous, then you can approximate it with a polynomial. So to begin explaining this to you, let me sketch some function f of x that you don't know anything about except the derivatives. Now initially, we're going to focus all of our attention to actually approximating this function at x equals 0. Once you know how to do that, there's actually a really clever trick that we can use to help you find it anywhere else. Now, to this function over here, we have the line of best fit here, and we already know that that's the same thing as the tangent. And then in my lesson on the second derivative, I also showed how to find the parabola of best fit as well. But now we're going to actually extend this to cubics, quartics, and basically anything you like, really. In theory, if you keep increasing the order of the polynomial that you use to fit the function, you're eventually going to get so close to the original function that you might as well have the original function. Now, in order to show you how we'd actually do this, I should show you with an example first, and then I'll do it in general. Okay, so here I have this function, minus 1 on x plus 1, and I'd like to find an approximation to it at x equals 0. Of course, I've chosen a really easy function for this just to make the computation as easy as possible. But in general, you can pick any function you like, and as long as you know its derivatives somehow, you can actually go ahead and repeat the exact same process we're going to find now. Now, just to make things a little bit easier to visualize, I'm going to start with a graph of this function. Okay, and then I'm also going to draw on the cubic of best fit as well. Okay, so this cubic over here is my attempt at drawing the cubic of best fit to this particular function f of x over here. Now, since we know that we want to approximate f of x with a cubic, we can go ahead and write down the equation of the cubic in the following form. Okay, so these a's over here are just constants. Instead of using different letters like a, b, c, and d, I've just labeled them with a subscript instead. This is actually going to be important for the general case, as you'll see later. Okay, so now we're ready for a really important point here. If we want to estimate this function here, it's not enough that the values are the same at x equals 0. We also need all of the derivatives to be the same as well. Otherwise, you don't really have the same function, do you? Now, if you take a cubic and you differentiate it 3 times, you're going to be left with a constant. So I'm going to go ahead and do that. Let me differentiate this particular cubic 3 times. Okay, so a lot happened there, but none of it was really complicated, so let me just walk you through it. When I differentiated the original function once, I ended up with a1 plus 2a2x plus 3a3x squared. When I did it again, I ended up with 2a2 plus 2 times 3, a3 times x, and when I did it one more time, I ended up with just 2 times 3 times a3. Now you'll notice that I didn't bother to multiply 2 and 3. I did do that on purpose, but you'll see why later on. So as we said, for this function to approximate this function over here, it's not enough for the function values to be the same, but all of the derivatives also have to be the same as well. Now, just to be clear here, in this particular case we already know the function, so there's not really much of a point in approximating it. Of course, in practice, anytime you use Taylor's theorem, you're trying to approximate a function you don't really know that well, but you somehow can measure its derivatives somehow. Now in this case, we don't need to measure the derivatives or do anything fancy. I already have the function, so let me go ahead and differentiate it 4 times as well. I'm going to start by writing it in a simpler form. Okay, so now that we have it in this form, it's actually really easy to differentiate this. So let me just go ahead and do it 3 times. Okay, so the same thing happened here. I just differentiated this function 3 times by using the bring the power down rule. Of course, I did use the chain rule, but the derivative of the inside is just 1, so I don't really need to do anything there. Okay, so now that we have all of the derivatives laid out like this, we're ready to tackle the problem. The first thing we can say is, if this is going to approximate this at all, you better hope that this value and this value are exactly the same when x equals 0. Okay, so on the left we want to find p0. That's pretty easy. If we just replace x for 0, you notice that this is 0, and this is 0. So you just get a0. And now we just want this to be exactly equal to f of 0. Well, we can do this really easily by replacing this x for a 0. When we do that, we get 1 reciprocal, which is just 1, and then we just get minus 1 when we do this. Okay, and now we also reasonably expect the first derivatives to be exactly equal to each other as well. Okay, so on the left over here, we can see that p dash of 0, again, is just going to cause this term and this term to cross out, so we just get a1. And then to find the right side over here, we just have to sub x equals 0 into this. Again, 0 plus 1 is 1, and then 1 to the power of negative 2 is still just 1. Okay, and next we want the second derivatives to be equal. So we can find the left-hand side by subbing in x equals 0 into this equation, and then we notice that this crosses out, so we just get 2a2. And then on the right-hand side, we just sub in x equals 0 into this equation, which just gives us 1 to the power of negative 3, which is still 1, and then we just get negative 2. Now, of course, these 2's just cross out with each other, so of course a2 just equals negative 1 as well. And now finally, we expect the third derivatives to be equal to each other as well. Okay, so on the left-hand side, we just sub in 0 here, but there's no x, so we just get 2 times 3 times a3. And then on the right-hand side, we can just sub in x equals 0 over here, and this just gives us 1 to the power of minus 4, which is still 1, so we just end up with 6. Now, of course, the 6 and this 2 times 3 over here do cross out, but I want you to notice that this over here is the same thing as f triple dash of 0. Now, this is going to be important later, as I said. And now that means we can just write out the final cubic in this form. Over here, I've just replaced a 0 for minus 1, a 1 for 1, and so on. Now, this is actually a really simple equation that I picked over here, because this pattern is just going to continue forever. But of course, this isn't always going to happen, so depending on the function you have, you may get totally different results. Okay, so now that you've seen how it's done with a specific case, let's repeat these exact same steps for a general function, and you'll see that it's really not that different. Now, the first change I'm going to make is that the polynomial doesn't really need to just be a cubic. So let me go ahead and actually write a general polynomial that has as many terms as you want. Okay, so I always find it really scary when I see things like this. But let me explain it to you. It's just the same as we did before. These a's are just the coefficients, and we want to find them in order to find the polynomial best fit to this function f of x. So if we just repeat the exact same steps as before, we'll end up with a general term for ak, and this allows us to find any one of these terms in basically an instant. So again, what we'd like to end up with is some formula for the kth term. If we have that, we can find any other term very, very quickly. Okay, so let's just repeat the steps again. We want to make sure that the function at f of 0 is exactly the same thing as p of 0. Okay, so just like we saw in the example, when we sub in x equals 0 into p, we notice that all of the terms cross out except for this first one over here. So p of 0 is of course just equal to a0. And since we are assuming that we know the value of f of 0, just like we did in the example, I just copied f of 0 to the right-hand side. Okay, but we said it's not enough for p of 0 to just equal f of 0. We also need the derivatives to be equal as well. So let's go ahead and force the first derivative to be equal as well. Okay, so to figure out what the left-hand side equals in this case, we're going to need to differentiate this function. So let me copy it down to the bottom and just differentiate it one time. Okay, so here we just repeatedly use the bring the power down rule. You notice that the constant crosses out, the x crosses out, the 2 comes down, which is what we see here, and then this just continues all the way through. Okay, and so if this is true, then subbing in x equals 0 into this term over here will just cause all of the terms with an x to disappear, and all you'll be left with is this a1 on the left-hand side. Okay, so after doing this, we've already found the first 2 terms in this polynomial. But I'm just going to do this 3 more times, because if I do, you'll be able to easily spot the pattern that's actually going on here. So let's just differentiate this again. Okay, so this time we're actually going to force the second derivatives to be equal to each other. Okay, so looking at this again, if we sub in x equal to 0, all of these terms cross out yet again, and the only term left over is this 2 times a2. Okay, and now this is where things start to get a little bit interesting. I'm going to go ahead and divide both sides of this equation by 2. Okay, I'd forgive you if you can't see the pattern yet, but things are about to become really clear in just a moment. But before we go any further, I'm going to replace all of the dashes over here for an alternative notation. Okay, so this notation just lets us stop writing dashes, and instead we just write the number of times we've differentiated in the brackets. Okay, so let's just go ahead and differentiate the bottom function again. Okay, so if this is true, then subbing in x equals 0 over here will also cause all of these terms to go to 0 again, and you'll only be left with 2 times 3 times a3. Okay, and now I can just divide both sides by this 2 times 3 to get the value of a3. Okay, and now I hope you can see the pattern brewing at the bottom over here. But just to confirm, I'm going to go ahead and differentiate this one last time. Okay, so this is the last stretch here. We're going to expect P4 of 0 to be exactly equal to F4 of 0 as well. Okay, so I don't actually need this term at the bottom here anymore, so I'm going to get rid of it. But I want you to notice this k times k minus 1 times k minus 2 times k minus 3. It's going to be important in a second. Okay, so let's again divide both sides by this term over here. Okay, so far it's looked like a lot of number crunching, but here's the pattern. It's actually pretty straightforward. Notice that we have the 2 over here and we have a 2 here. Then in the next term we add a 3 because this was a 3. Then in the next term we add a 4 because this was a 4. To make this even clearer, I'm going to divide this term by 1 and add 1s in front of all of these as well. Okay, so this 4 times 3 times 2 times 1 is something that shows up a lot in maths, so we give it a name. We call this 4 factorial. We indicate that we have a factorial with this exclamation mark over here. Okay, so following the same pattern, this 1 times 2 times 3, well, that would just be 3 factorial. And then similarly, this 1 times 2 is just the same thing as 2 factorial. And then 1 on its own is just the same thing as 1 factorial. Okay, so we just come to this conclusion here. If we want the coefficient of x to the power 4, then it's just this a4, and we get it by differentiating 4 times, subbing in 0, and then dividing by 4 factorial. The same is true for absolutely any other coefficient. But you might wonder, then, why isn't it true for this one over here? Why isn't this divided by 0 factorial? Well, actually, it is, but I just didn't write that yet, so I could explain it to you. To go from 4 factorial to 3 factorial, don't you just divide by 4? Look at that. And to go from 3 factorial to 2 factorial, again, you just divide by 3. To go from 2 factorial to 1 factorial, divide by 2. And to go from 1 factorial to 0 factorial, divide by 1. But 1 divided by 1 is still 1, so 0 factorial is also 1. Okay, so at this point I hope you can see that if you wanted to find the coefficient of x to the power of k, which is just ak, you just use the same formula. Differentiate k times, sub in 0, and divide by k factorial. Okay, and now this formula over here is actually Taylor's formula. You could just go ahead and use it without even bothering to do any of this work, but you would need to find the kth derivative, so it's pretty much equivalent to just doing the work anyway. Now, if you're anything like me, you might actually find this a little bit unsatisfying. I mean, it's great and all that we can find polynomials of best fit at x equals 0, but what if we wanted to find polynomials of best fit at other x values instead? Well, in order to be able to do that, we're going to need to generalize this formula to be able to work at any value of x, rather than just x equals 0. To be entirely honest with you, this particular formula over here is a special version of Taylor's theorem, and it's called Maclaurin's theorem. Maclaurin's theorem is basically Taylor's theorem written at x equals 0, and that's the reason why 0 appears in the formula. In a follow-up lesson to this one, I'll show you how you can actually generalize this formula to work at any x value rather than just x equals 0. But at this point, I'd like to summarize this lesson. In this lesson, we learned about a special version of Taylor's theorem, known as Maclaurin's theorem. Taylor's theorem basically says that if we have a random function, like this f of x over here, we can approximate it with a line of best fit, a parabola of best fit, a cubic of best fit, or basically any polynomial we like. The trick to doing that is first writing out the general polynomial that we want, and then differentiating it a whole bunch of times. For this polynomial, a0, a1, a2, and so on are the coefficients of the polynomial. And if we're going to write the general polynomial, we just need to find the values of a. So in this lesson, we did a specific example where we found these a values for a specific case, and then we showed how to do it in general. We found that in general, the kth coefficient is given by differentiating k times, subbing in 0, and then dividing by k factorial. And remember, k factorial is just what you'd get if you multiplied a whole bunch of numbers. For example, 4 factorial is 4 times 3 times 2 times 1, and 10 factorial would be 10 times 9 times 8 times 7, all the way down to 1. Now the trouble with this version of Taylor's theorem, which is often called Maclaurin's theorem, is that it only works at x equals 0. But in a follow-up lesson to this one, I'm going to show you how we can take this formula and then rewrite it so that we have the line of best fit, the parabola of best fit, and so on at any x value that we like. So you should tune in to that next lesson where we talk about this generalized version of Taylor's theorem. But at this point, I'd like to end this lesson on Taylor's theorem. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.